Hi, in this video, we're going to take a look at spectral densities for time series. All right, so the big idea here is that we're going to come up with another way of solving problems with time series. So when I'm trying to do like my theoretical construction of time series to understand them better, we're going to use Fourier analysis to get a new tool to tackle problems. Now, up until now in the video series, we have been looking at autocovariance as a tool for us to analyze our time series. What we're going to do is that we're going to apply the Fourier transform on the autocovariance, and that will give us our spectral density. And something that's nice about this is that the spectral density, if I do the inverse Fourier transform, it'll give me the autocovariance. We can go back and forth. And so why do we care about this? Well, if I have a problem I need to solve, I need to figure something out, I have two tools to work on it with. So one of these is going to be better, going to be easier for whatever problem I'm working on. I'm going to pick the easier one of the two. All right. So if I have a problem that involves lags, I'm going to be using autocovariance. If I have a problem that requires us to have like a periodic point of view as we do our analysis, I'm going to use spectral density. All right. So we're going to go over some examples from time series analysis and its applications. Here are the authors' names. Here's our GitHub page. And University of Central Florida students can download the textbook for free through the library. All right, so let's take a look at this. So spectral density, this is a fundamental tool for us to analyze time series frequencies. All right, and so we're going to look at the spectral representation for stationary processes in this video. Now, Wold decomposition justifies the use of regression in analyzing time series. Now, the spectral representation theorems supply the justification for decomposing stationary time series into their periodic components, where we're going to have things appearing in proportion to the underlying variances. All right, so as an example, consider this periodic stationary process where we just have one frequency, this omega sub 0. And we have a sine and a cosine component to it. And the coefficients of sine and cosine are uncorrelated zero mean random variables with equal variance. All right, well, the number of time periods needed to complete one cycle is going to be 1 over omega sub 0. And the process is going to make omega sub 0 cycles per time interval when I look at this individual component. Where we're going is that we're going to have multiple of these, like adding up to our actual time series. Now, as we work through this, we're going to be using a lot of complex numbers. If I'm doing Fourier analysis, you can bet your hat that we're going to have a lot of complex numbers and a lot of trigonometry going on. And that's going to happen here in this video. All right, so here are some useful complex identities. First and foremost, this is Euler's formula, where e to a complex I times, some angle is going to be equal to this cosine and sine representation. Notice that cosine is the real part and sine is the imaginary part. Well, if I take this formula from Euler, I can rewrite this in a certain way, and I can see I get a formula to represent cosine in terms of exponentials, and I can represent sine in terms of exponentials also. Now, notice that there is an I on the bottom in the denominator of that fraction. All right. Now, something that will come up when we're dealing with the sine formula in a little bit is that 1 over sine is equal to negative I. If you multiply them out, I times I is negative 1, then that negative sign will cancel out that negative 1. So that means it's the inverse. All right, so if I take Euler's representation of cosine, we'll get very naturally that the autocovariance for my process that we were just looking at is going to be sigma squared times cosine of 2 pi times my omega times the number of lags. Okay, well, I can rewrite this in terms of those exponentials. Now, when I get to this stage here, as I look at that, there's a fundamental identity in your complex numbers course that says that this will be equal to e to this power here, integrated with respect to this capital F of omega over negative 1/2 to 1/2. And so the variable of integration here is the omega. And so as we work through this, we're always going to be saying that our omegas go from negative 1/2 to a positive 1/2 throughout. And so here, this capital F of omega is our spectral distribution function. Okay, well, the spectral distribution function for this particular example is going to have 0 when omega is less than negative omega sub 0, sigma squared over 2 when omega is between negative omega sub 0 and positive omega sub 0, and the spectral distribution function is going to be equal to sigma squared when we have a larger value of omega. Okay, so you'll notice that capital F of omega behaves like a two-value discrete cumulative distribution function, except it's increasing to the variance instead of to 1. All right. So let's take the spectral representation of an autocovariance function. All right, so if our time series process is stationary, and here's our autocovariance, then there exists a unique monotonically increasing function, capital F, called the spectral distribution function with these properties. First and foremost, f of negative infinity is equal to f of negative 1/2, which is equal to 0. F of 1/2 is equal to f of infinity is equal to gamma of 0, my autocovariance at 0 lag. Okay, now notice that I'm not saying anything between negative 1/2 and 1/2. We're saying that it is monotonically increasing, and that's not strict. It's not strictly increasing, but it's just increasing. So whatever's going on is what's going on. And gamma of h is going to be equal to the integral where I put the df. I dropped, this should appear here. That is a typo on my part. All right, so the integral of gamma, the autocovariance of gamma is equal to the integral from negative 1/2 to 1/2 e with respect to the spectral distribution function. And so when I take, the appropriate rescaling, I can integrate with respect to dw, or d omega, I should say, and that will give me my autocovariance function. All right, so now let's take a look at the spectral density. If the autocovariance function is absolutely summable, so here I'm saying that if I go through and I add up the absolute value of all of my autocovariances from negative infinity to positive infinity, if I add them all up, I get a finite number. Then we have this representation for our autocovariance. Our autocovariance is equal to this integral, which is similar to what we just looked at, negative 1/2 to 1/2 e to this power. Here is our spectral density, and we're integrating with respect to omega. And here, of course, for autocovariance, we're talking about the integer values. And so if I look at that, I'll go, hey, that looks a lot like a Fourier transform. Okay. And if I can go up and I can take the inverse transformation also. When I take the inverse transformation of my autocovariances, so multiply by this E business, add them all up, I get back the spectral density. So we could go back and forth between autocovariance and spectral density freely to be able to solve a problem. So if I'm working on something and I'm like, man, it would be a lot easier if I was dealing with spectral density, I can convert over, solve it. If I'm working on a problem, I go, man, I wish that autocovariance was here. It would be much easier to solve the problem that way. I just, boom, move over to the autocovariance function. I can go back and forth freely. and use all the properties of Fourier transforms. Now, it works out that when the autocovariance function is non-negative, the spectral density is also non-negative, and spectral densities are even functions. So f of positive omega is equal to f of negative omega. So typically we only plot the positive axis when we are plotting spectral densities, just to give ourselves a little bit less to look at, a little bit less to interpret. So if I take the formula I was just looking at, and I set h equals to 0, I can see that the variance of my time series process is equal to the spectral density integrated over -1/2 to 1/2. All right, so this gives me another way to compute variance of my time series. So this expresses the total variance as the integrated spectral density over all frequencies. All right. Now, a linear filter can isolate the variance in certain frequency intervals or bands. And so really, the true punchline of this video is that autocovariances express the information of the time series in terms of lags, while spectral densities express the same information, but in terms of cycles. So if lags are easier, autocovariance. If cycles are easier, spectral density. I get to pick and choose. I get to pick the way to solve the problem, whichever is easiest for me. So some problems are much easier if I solve it using the lagged approach, but others are going to be much easier if I am more concerned with the periodic information. And so it's an important thing to remember is that the autocovariance and the spectral density are Fourier pairs with each other. All right, so now something that is important in this lane is that anytime you're dealing with mathematics, mathematicians love to check, is it unique? Does it exist? Is it unique? We just fixate on this. It works out that for all practical purposes up to uniqueness in integrals to absolutely summable autocovariance functions are equal, then they have the same spectral densities. So if I have two autocovariance functions and they are absolutely summable, then they have the same spectral density. So what this does, makes it so that there's no ambiguity on what I'm working with. That if I do the transformation, I know that I'm not going to get bounced to a different presentation than what I want. And something to note is that autoregressive moving average models are always summable. So this gives us a uniqueness aspect to our autoregressive moving average functions. All right, so let's go look at that example. Let's take a time series where it's strictly white noise. We just have random noise coming out. And so my observations are uncorrelated. They have constant variance. And so, of course, the variance of zero lag is going to be just the variance of the system. It's white noise. So the autocovariance is going to be 0 when I have a value other than 0. This should be an H right there. It's a typo. And so if I sit down and I work through this, if I take this summation, most of these are equal to 0. Okay, so only one that's not 0 is going to be equal to at lag of 0. And so, we're going to get this. So this process contains equal powers for all frequencies, and it contains all different frequencies in roughly an equal mix. And so this is why we call it white noise, because when we talk about white light, all frequencies in the color spectrum are at the same level intensity. Since we have the same level intensity of all frequencies in this example, we call it white noise, and that's where the name comes from. All right, so let's go ahead and take a look at this. So what we're going to do is I'm going to just plot the ARMA spectral density function, which is in the ASTSA package. And now, as a default, it sets it up so that the polynomial for my auto regressive portion and the polynomial for my moving average portion of the model are both 1 by default. And so you'll notice I don't actually put any parameters in there, so I just leave it alone because it's the just a white noise model. And so the default settings of this are white noise. So when I look at this, you'll notice I have a constant value right at where we have the variance for our white noise process. Now let's think about a convolution. All right, so if I take a convolution where we take coefficients times points of our time series value, and the coefficients are absolutely summable, then what we're going to do, we're going to call the set of A's the impulse response function. And if I do a Fourier transform on the impulse response function, we will get this function here on omega. So now, here is the output spectrum of a filtered stationary series. We're going to use this in a moment to work out some details and to show how valuable this property is. All right, so if y sub t is equal to the convolution of another time series, and the convolution is absolutely summable, and x has a spectrum density function, then the spectrum of y is given by this formula, where I take that a that we talked about a moment ago, take its modulus and square it, and then multiply by the spectrum density function of x sub t, and we can rewrite this just a little bit more explicitly here. All right, so now let's prove this. How do we prove this? What we're going to do, we're going to start with the covariance function, all right, for y. So this is a covariance of y. I'm going to replace the terms of y with their x representation, so as a convolution. Now, I am dropping a few terms from the summation notation just to make this a little bit cleaner, at least a little bit easier to read. Now, I'm going to use the covariance formula on this. And so I realize I've got a summation coefficients. I have a summation and coefficients. And so I know that I can factor these out of the covariance formula. And so now I've got the covariance on the time series x multiplied by the coefficients, and then I'm adding everything up. All right, so I'm going to replace the covariance with the autocovariance function on x. All right, that's easy peasy. So now I'm going to realize that I can reverse this item using the Fourier transform. So I know that this is what I get back when I apply the Fourier transform on the spectral density of x. So boom, I'm going to invoke that. So I take this autocovariance, I convert it over to its representation as the Fourier transform of the spectral density. Okay, so now I'm looking at this, and I realize that I have, with respect to integration, I can rewrite this out. So what I'm going to do, I'm going to take the integration and I'm going to pull it out front. So we're going to have a little bit of assumptions here about taking an infinite sum and moving it inside an integral, but for this particular situation, it works out. I got to bring the coefficients in, and I'm just going to rewrite this integral with the sum and coefficients on the inside of the integration. All right, so here I've got this and I've got this. So you'll notice also on this step, I went ahead and broke up this s, negative r, and h into the product of 3 different exponentials, okay? And then I move the exponentials around to match up with those coefficients. All right, so now basically just reorganizing some things that here I've got a -2 and a -I here. I'm making sure that things line up. Now, when I, because I need to have a negative up there to have the proper Fourier transform presentation. Actually, it doesn't matter which version of we would have as long as I'm consistent throughout. To be consistent on my Fourier transform, I need that negative sign here. So to put it there, I replace I with negative I, and then I put a negative sign out front. All right, so now when I look at this, I realize that this is that A of omega, and this is the conjugate of A of omega. Huh, okay. So if I take complex number multiplied by its conjugate, isn't that its modulus squared? Yes, it is. And so here I get the modulus squared of A. And so now that takes me all the way. I've got the proof done. Check that out. Now, by the uniqueness of the Fourier transform that we just talked about a moment ago, this has to be the spectral density for the time series Y. All right, so this gives, so if I have a time series and I want to get spectral density, and I know that the time series is a convolution, a linear combination of another time series, I can go and I can work this out, figure out what I actually, figure it out using the time series that is inside the convolution. All right, so if we look at this, it's going to work out that if I have an autoregressive moving average model, and I've got phi and theta as the polynomials for autoregressive and moving average, the spectral density is going to be given by this formula here. And this is basically just rewriting what we talked about a moment ago. All right. And so let's go ahead and use this. And so let's say that I have a moving average model. This is a pretty simple moving average model that we have 1/2 times the previous white noise plus the current white noise is equal to my current time series observation. All right, so here's my polynomial on the moving average part. And in previous videos, we've talked about the autocovariance of this. So here are those values here. Something that's super important to us is that for larger values of h, plus or minus, the autocovariance is going to be equal to 0. And so what I'm going to do is I'm going to take that spectral density formula that we have. So I'm going to take this formula, and I'm going to replace my autocovariances with the values I have here. Notice that the vast majority of them are 0. So I have plus or minus 1 and 0 are the only lags I don't have 0 on. So I just slap them in. Boom, easy peasy lemon squeezy. All right, well, once I do that, I get this, and I realize I have coefficient. Coefficient is the same value here and here, and I've got an e business going on. I have e to a negative something and e to the positive version of that something. I know I can replace this with a cosine, so I do it. And so now I have the spectral density function for this. Now, we can do this another way, because I just gave you a formula for working out what this is. All right, so let's invoke that. Let's use that autoregressive moving average property that I'm going to take the autoregressive portion, and I'm going to take the moving average polynomial, put it up top, put e in there, take the autoregressive polynomial, put it on the bottom, put the e inside that here. All right, so this is just 1, so that doesn't do anything for us. And so now I'm going to work this out. I'm going to take my moving average polynomial that we have up here. Here's that moving average polynomial. I plug that in for here. Boom, we get that. And so now, and notice I have e instead of a z in there. And so now I'm just going to compute the absolute value, which is squared, the absolute value squared, which is the product of it with its conjugate. All right, so to do that, I'm just going to do some multiplication. And you'll notice that when I do my multiplication here, I have opposite signs in the exponents. That's because they're conjugates of each other. All right, so then I do my multiplication, first, outer, inner, last. I'm using FOIL, just like in college algebra. And boom, I get exactly the same thing. So we've got 2 ways to solve the same problem. So going forward, whenever I have a problem, I'm going to pick the one that I feel is going to be easier when I tackle this. All right, so now let's go ahead and plot this. So applying the spectrum for unit variance shows that the lower or slower frequencies have greater powers than the higher or faster frequencies. And so we can see this declining slope right there, and that is, in fact, a cosine curve. All right, so now let's go ahead and hit a second order autoregressive series. So here, the authors of the textbook just said, hey, this is the example I want to run with. And so here it's second order. Notice I've got x of t. I've got lag of 1, lag of 2. And then I have my moving average part. And so here, this is going to be my autoregressive polynomial. And my moving average polynomial is just going to be 1. So let's invoke that formula that we just used a moment ago. So I'm just going to write down the formula right here. I'm going to plug in the polynomials with the E business going on. Well, I know that the moving average polynomial is just 1. Boom, I've got that. On the bottom, I'm going to put in the autoregressive polynomial, put that here. And now I need to take the modulus and square it, which is equal to taking the item itself and multiplying by its conjugate. So I'm going to do that. And so now I have worked out what the spectral density is going to be. All right, so now this is kind of complicated looking, kind of ugly, right? That we have a constant up top, and then we have something here, and then we have a cosine, another cosine. And so that there's quite a bit going on here. If we sit down and we work on this, we'll see that this is going to be unimodal from negative 1/2 to positive 1/2. And it's going to have a peak around 0.16. So here I can use the autoregressive moving average spectral density function in ASTSA to figure out what the plot is. Now I actually double checked this value. I took that function and I worked out, and well, I plotted values after just explicitly computing things, and I got in fact the same result. Now we can compute this using lags also, easy peasy lemon squeezy, where we start by just taking the auto covariance function here, and then I'm going to replace the white noise with the auto covariance side of the equation, and then I'm just going to go through and just start slugging this out. So I did this manually. I worked out all the details on this. I did this on Sunday morning. I expanded out this whole thing by hand, and then simplified things so the proof didn't get too long. And so I'm going to end up getting this. And so now when I get to this step here, I'm going to go through, I'm going to group items with similar lag. So I'm going to have the h plus 1, h minus 1. I'll have the h plus 2, the h minus 2, and you notice I'm grouping like terms. You notice I have the same coefficients here. All right, so now what I'm going to do, I'm going to replace each of these auto covariances with their Fourier transform representation, okay? And so I'm going to go through and do that. So here I replace this with this integral. I replace this with these two integrals. I'm going to replace this with these two integrals, and it goes over here. I have to scroll to the right. All right, so then I'm going to go through and I'm just going to simplify things. Now you'll notice that in all of these integrals I've got a bunch of integrals, but I'm going to put them all together into one big integration. Now, when I look at this, notice I have an h every single time in each of these e's. And so what I'm going to do, I'm going to factor out the portion of the exponential with the h, and I'm left with all of this left over. Now, I look at this and I realize that, hey, that looks a lot like cosine. Hey, that looks a lot like cosine. I'm going to replace these with cosine appropriately. You'll notice I'm going to be multiplying by 2 when I do this, and I get exactly the same thing I had before for my spectral density function. It works either way if I use lags or spectral densities to compute this. Oh yeah, and so I haven't quite taken this all the way. I jumped the gun on this. Well, I know that the spectral density of white noise is going to be equal to a constant, and so I know that one side is equal to the other side on my autoregressive moving average process, and so the sigma constant is equal to all of this over here because I know that they're equal to each other left and right side. And by the uniqueness of spectral densities, these have to be equal. Therefore, I have to, if I divide out by this, I'll get the result I'm looking for. All right, so now let's consider the situation where I have an explosive time series. All right, so realize that if I go with this autoregressive degree 1 model, that coefficient is greater than 1 in magnitude. And so what's going to happen is that the time series is going to blow up and it's going to get big after a few iterations. Okay, well, don't we have a connection between explosive time series and well-behaved time series? Yes, we do. What we want to do now is that we want to use density formulas to figure out what is the well-behaved representation, the stochastically equivalent time series that is well-behaved instead of explosive. All right, so what I'm going to do, I'm going to invoke that autoregressive moving average spectral density property here. So you'll notice that I've got 1 for my moving average polynomial, and I've got 1 minus 2 for my autoregressive polynomial. So I put them in the appropriate positions. Okay, so I've got that. I'm in a good position. Now, what I'm going to do is I think about it, and I realize that every single polynomial we have in autoregressive moving average, we always have a 1 for a constant. So what I'm going to do is I'm going to look at this, and I want to factor this in a manner that's going to set it up so that I have a new 1 inside the modulus absolute values. All right, so I'm going to look at this, and I realize I want to factor this -2 times e. If I can factor that out, I'm going to be left with a 1 in this position. Okay, so now this looks like an autoregressive polynomial in the spectral density property. Now I've got this thing left over. Well, remember, the absolute value or the modulus of a product is a product of the absolute values. Okay, and so I'm going to invoke that this is, when I factor out the absolute value part, I factor out across the absolute values, and I take the modulus, I'm just going to get a 4 right there. And the reason for it, the 4 is because there's a square. So now I have rewritten this in another presentation. So now I have this, that looks like a well-behaved autoregressive polynomial. Here I've got nothing going on for the moving average polynomial aspect, and I've got a 4 to rescale the variance. So let's rewrite this. So now if I look at that, I realize that I can connect this back to a time series process where we have an autoregressive formula right here. And now my white noise variance is 1/4 of what it was before. And these are stochastically equivalent time series. Okay, so let's keep on working on this. So let's consider another stationary process, just like we talked about at the beginning of the video, that we have uncorrelated random variables times sine and cosine for given omegas. Okay, and we're going to say that we Coefficients are uncorrelated. They have expected value 0, and they have the same variance. All right, so I'm going to take what I have here, and I'm going to rewrite my time series using Euler's formula. Okay, so once again, I'm just doing this whole sine cosine trick like I did before. So I'm going to replace this cosine with the exponentials here. I'm going to replace the sine with the exponential here. Okay, and then I'm going to rewrite it doing grouping like terms on the e's. We're going to group like terms. All right, now when I get to this point, what I'm going to do is I'm going to say, you know what? I'm going to call this Z. I'm going to say that this is just Z to make my life a little bit easier, make it a little bit more compact. And when I look over here, I realize that, hey, that looks a lot like Z, except we have a negative for the imaginary part. It's the same as Z, except negative on the imaginary part. That means they're conjugates of each other. And so this is Z, and this is the conjugate of Z. All right. And so now I can go ahead and take the expected value of Z, which is 0. And, the conjugate of 0 is 0. So the expected value of the conjugate is also 0. And so now let's take a look at covariance on complex numbers. Well, the covariance on complex numbers is going to be the first one times the conjugate of the second, take the expected value. Okay. And so now if I want to take the variance of Z, well, that's just Z, Z times its conjugate, like that, under this notation. And I can rewrite this out, and I can see that the expected value, the variance is going to be sigma squared over 2. So that gives me the variance of Z. Okay. Now let's go ahead and compute the covariance between them. I'm using the same trick I did a moment ago, where I have Z times the conjugate of the conjugate this time. So here, remember, in the second position, I take the conjugate of the item. Well, the item is the conjugate of Z, so I have double conjugate. They cancel out. When I multiply this out, over here, we're going to get a negative value. The cross term is going to give us a 0, and everything's going to cancel out. And we can see that the covariance between Z and its conjugate is equal to 0. All right, so now let's go ahead and do a replacement. So I'm going back to the original process. Here's my original process. Here's it represented using e's initially, replacing sine and cosine. Now I replace the coefficients with Z, and I look at this and I go, hey, that looks like a formula I learned in complex numbers. That's equal to this special integral. All right. And so this Z of omega is a complex value random process that makes uncorrelated jumps at negative omega sub 0 and omega 0, and has mean 0 and a variance of sigma squared over 2. And so, just continuing on with this, if X is a mean 0 stationary process with spectral density function F that is unique monotonically increasing, and we have 0 from negative infinity to negative 1/2, and positive 1/2 to infinity gives us the variance of the time series, then there exists a complex value stochastic process Z on where the interval omega between negative 1/2 and 1/2 having station or uncorrelated overlapping increments, such that we can write using a stochastic integral. That's a lot to say. And now once I have the stochastic integral, we can start using this, and we are able to compute the variance on the difference of values of Z using that spectral distribution function very nicely. And so that is the spectral representation of our stationary process. All right, well, this is all I've got for you. Take care, and life is short. Do math.